Welcome back to our series on Introductory Statistics. My name is Mark Ledbetter. We are in Chapter 7, and we are doing Section 7.6 in this video. This video is going to talk about the normal approximation for the binomial and p-hat distributions. So our topics are going to include something that's extremely important, and those are the assumptions or the requirements that are needed in order for us to use the normal approximation to the binomial. You cannot use this in all cases, so it's extremely important to understand these requirements. And as always, I will be placing an emphasis on those so that you as students, if you go to a next course or if you don't go to a next course and you need to use this information, that hopefully I will impress upon you the need to come back and check your requirements. All right, we're going to learn how to compute the mean and the standard deviation for the normal approximation using the binomial. And this is also very important. We're going to have to learn how to use something called a continuity correction. And then how do we convert x values to a range of z-scores, x values from the binomial to a range of z-scores. And then we need to find the sampling distribution of p-hat. So the first thing is that we're going to talk about the requirements. Now, if you remember, we have the binomial distribution, and it has, authors like to break this up into 4 requirements. They're really 3, but we'll talk about that. The first is that we divide outcomes into 2 categories. The one of interest and all others grouped together. That's number 1. Number 2 is that we have something called Bernoulli trials. So we have repeated trials that are independent of each other. This means that the probability of getting an outcome in the category of interest, or the category we're interested in studying. Some people call this a success, but again, calling it a success may lead you to confusion if you're studying something that's undesirable, like death or a disease. So I try to avoid that terminology, but the book will certainly have that in there, and so will some of the problems. The category of interest can be called a success, and I will put that in quotations just to say that it is maybe not really a success. It's just the outcome of interest has occurred. And so the fourth thing that may seem really trivial but is important is that the number of trials n is known. Now, we could flip a coin until we get the first head, and so the number of trials there is not known. Or we could roll a die until we get 2 6s in a row. Again, we don't know how many rolls we'll have to do to get 2 6s back to back. So these are the requirements for the binomial distribution. And then here are the requirements for us to use the normal approximation. N times P, remember this probability of getting a category of interest, this is called P, and Q is equal to 1 minus P. So in order for us to be able to use this approximation, we have to have that N times P has to be greater than or equal to 5, and N times Q has to be greater than or equal to 5. So this tells us that we have to have at least 5 outcomes in each category. Okay, so at least 5 results in each category. And that pops up on me every now and then. All right. So to use the normal approximation, if x has a binomial distribution and n times p is greater than or equal to 5, and n times q is greater than or equal to 5, then we're going to calculate mu as np, and sigma will be the square root of npq. This is the mean, binomial mean, and this is the standard deviation of the binomial. And it makes sense that we take the mean and standard deviation of the binomial and use those as the mean of the normal distribution, because we would hope to have a normal distribution with exactly the same mean and exactly the same standard deviation. So we can approximate the binomial using the normal distribution that has a mean of mu equals np and a standard deviation that sigma equals the square root of n times p times q. Okay. So let's do an example where we have n is equal to 10, p is equal to 0.75, and x has a binomial distribution. The first thing we need to do is test that n times p is at least 5. So n here is 10. P is 0.75, that's going to equal 7.5, so yes. We also need for n times q to be at least 5. Well, n is still 10, q is going to be 1 minus p, which is 0.25. This is only 2.5. So this does not meet the requirements, and so we cannot use a normal approximation for the binomial in this example. We would have to use the binomial itself and calculate exactly all the probabilities. Okay. Now, a discrete distribution only has a probability at each value of x. So we could draw this like here is 0, and we might have a probability if this is prob. And then at 1, we might have a little bit more, and at 2, we might have some more, and then so forth. There is no probability in between 0 and 1, in between 1 and 2. But if we're going to use a continuous distribution, probability distribution, like the standard normal, which is z, we know that the probability that z is equal to any value a is exactly equal to 0. There is no probability at any point. We have to have an area. So how are we going to use a normal distribution to estimate the probability that x is equal to some value, say c, in the binomial using the normal distribution? Well, someone was very clever, and what they decided, here is a probability distribution, and a binomial probability distribution with, I believe, p equals 0.5. And so we have, I don't remember what n is, but we have 0, 0, 0.003, 0.014, 042, 092. Notice what we've done here. We've drawn a histogram, a probability histogram for discrete distribution, and we're drawing it from the halfway point below 0 to the halfway point above 0. And then the same thing, we're drawing a bar around 1, starting at 0.5 and going to 1.5. So we make it look like the probability is spread out around the number 4, let's say, or around the number 5. Each number, we make it appear as if the probability is spread out around that number, going from halfway between the previous number and halfway to the number above that number. So we're going from 3.5 here to 4.5 to represent the probability around 4. And so someone very smart decided, well, let's use something called a continuity correction. Here n is 15 and p is 0.5. That's right. Okay. N is 15. We should know that here. And p is 0.5. So we're letting the probability around 5 look like it's spread out between 4.5 and 5.5. Okay? Now this continuity correction is very technical, so there's some specific and special rules that we have to use in order to use it. And so the signs are extremely important. They change how we use it. So let's say we want to find an approximation for the probability that x is equal to 5 when n is 15 and p is 0.5. So first thing we do is we check our requirements. We've got n times p, 15 times 0.5 is 7.5, that's greater than 5, good. N times q is 15 times 1 minus 0.5, that's still 15 times 0.5, that's another 7.5. Notice that this number and this number, they have to add up to n, which is 15. So if we need 5 observations in each category as a minimum, we can't use this approximation if n is less than 10. We can only use it for n equals 10 when p is equal to 0.5. That's the only time that we have n times p equals 5 and n times q equals 5. So n has to be a minimum of 10 for us to use the normal approximation. Or np greater than or equal to 5 and nq greater than or equal to 5 cannot be true. So if you see that n is less than 10, you know right away the requirements have not been met. We can't do this. However, if n is greater than or equal to 10, you still have to check n times p and n times q to make sure both are at least 5. Okay. So what we're going to do here is we're going to calculate mu and sigma. So mu is n times p, which we just found was 7.5. And sigma is the square root of n times p times q, which is the square root of 375, which is about 1.936, which will round to 1.94. Okay? Then what we're going to do is, in order to find the probability that x is equal to 4, this is the same thing as the probability that x is between 4.5 and 5.5, because there is no probability between 4.5 and, I'm sorry, this is x is equal to 5. Yeah, x is equal to 5, not 4. So the probability that x is equal to 5 is the probability that x is between 4.5 and 5.5. There is no probability from 4.5 to 5, or from 5.5 to 5, or from 5 to 5.5. There's only probability at x equals 5. So, but in order to do this, we're going to have to use 4.5 and 5.5, or else we won't have a range of values for the normal distribution, and we have to have a range of values to have a probability. So we have 4.5 minus 7.5. This is the mean, so we're using the formula of z. Z is equal to x minus mu over sigma. So 4.5 minus mu, which we said was 7.5, divided by 1.4, which is sigma. And then we take the upper number, 5.5, minus the mean, 7.5, divided by the sigma, and we get p of the probability that z is between 1.55 and negative 1.55 and negative 1.03. Both these numbers are below the mean of 7.5. Now we look up the probability in the z table with the largest number, which is negative 1.03. We get a probability of 15, 15, or 0.1515. We then look up the smaller number, negative 1.55, and we get a probability of 0.0606. We subtract these, and our answer is 0.0909. The actual value from the using the table, the binomial table, is 0.092, so this is pretty close. A very nice approximation, actually. So 0.091 versus 0.092, not bad at all. Okay, so what we used here was a continuity correction, 4.5 and 5.5. We used it around the value 5, and we had equals to. So we will stop here for this video, and when we come back in the next video, we'll do some more examples with the continuity correction. We'll go over some rules that you need to know in order to do this correctly every time. I'm going to give you the answers so that you don't have to struggle to remember, well, which way do I go? What do I do in this situation? All right, so that's it for this video. Please take care of yourself. Stay safe because we want to see you here next time.